Independent events don't affect each other, such as rolling a dice twice. The first roll, the outcome of that, whatever number you get, has no impact whatsoever on the second roll. What about these pairs of events? So for throwing a head on the first and a head on the second flip, they are independent events. Okay, the first event has no impact at all on the second event. Raining tomorrow and raining the day after, they're not independent events. If it's raining tomorrow, then it's more likely it would rain the day after that. They do have an impact on each other. Choosing maths at A-level and physics at A-level are not independent events. And you can see that because 6 out of the 7 students here at Oldfield who are doing physics also do maths. Have a garden gnome and liking pizza. As far as I'm aware, they are independent events. Having a garden gnome has no impact whatsoever on whether you like pizza or not. So if we know we've got independent events, we can calculate the probability of them both happening just by multiplying the probability of each individual event. For example, the probability of rolling a 6 twice in 2 rolls, well, rolling a 6 in 1 roll is a 1 in 6 probability. So rolling it again would be a 1 in 6 probability. So that gives us a 1 in 36 chance of a 6 twice in 2 rolls. On this example here, you can see this probability tree we've got going on, and that's a brilliant way to set out problems like this. Sometimes you're given the probability tree like this, sometimes you need to just think, hang on, that's a really useful tool, I'm going to choose to use that. So in this question, we've got 2 bags. In the first bag, there's 4 red and 6 green balls. In the second, there's 3 red and 5 green. A ball is taken at random from the first bag, and then a ball taken at random from the second bag. So these events are independent. Whatever she pulls out the first bag has no impact on the second bag. And within each of these, they are also mutually exclusive. So in the first bag, it can either be red or green. It can't be both, and it can't be anything else. They're exhaustive events. Now we need to work out the probability she takes 2 greens for the first part here. So let's think about what we can add to the tree diagram to help us. So in the first bag, there's 4 red and 6 green, so there's 10 balls in total. So the probability of choosing a red is the 4 red out of 10 in total. Probability of choosing a green is 6 green out of 10 in total. In the second bag, there's 3 red and 5 green, so we've got 8 in total. So probability of picking a red at random is 3 out of 8, and that's exactly the same probability that we put in here. Probability of picking a green is 5 out of 8. And again, because these events are mutually exclusive and they're exhaustive, the probabilities must add to 1, and we can see that here that we add these and they do add up to 8 eighths, they do add up to 1. So to work out the probability of 2 greens, there's a 6 in 10 chance to get green on the first one, 5 in 8 chance to get green on the next. So we multiply those. And this is where fractions are generally much easier to work with than percentages or decimals, which we can use for probability as well. So numerator is 6 times 5, denominator is 10 times 8, and we can simplify that. Second part is the probability she takes at least 1 green. Now there's different ways she could do this. She could pick 2 greens, at least 1 green, which we've just worked out the probability for. She could pick green on the first and red on the second, or she could pick red on her first and green on her second. So we've got these 3 different ways she could take at least 1 green. Now these events are mutually exclusive, so to work out the probability of at least 1 green, we could just add those together. An easier way to do it though is to see that that just leaves 1 possible outcome, okay, which is the probability of taking a red, then a red. So she's not taking any greens. Now, if we work out the probability of taking 2 reds, we subtract it from 1. That will give us the probability of taking at least 1 green, which is a bit more of a straightforward way of working it out. So for that, we need to follow this path, 4/10 times 3/8. So we need to do 1, take away 12/80, which we can simplify to 3/20. And that will give us 17 out of 20. So that's the probability of taking at least 1 green. Pause the video, have a try with this one, really similar. On this one, we have got decimals instead, but they're quite nice, straightforward decimals to play with. So we're told that the probability the bus will be late on any day is 0.2. So we can fill that into our probability tree. 0.2, it's going to be late, and that's the same on a Sunday as it is on a Saturday. Now we've got here our mutually exclusive events, and they're exhaustive. Either the bus is late or it's not late, can't be anything else. So this must be 0.8. These probabilities here must add up to 1. And it's going to be exactly the same here for the bus on Sunday. So we want to find out the probability that the bus is late on at least one of these days. So there's different ways of doing that. It could be late on the first day, not late on the second. It could be not late on the first day, but late on the second, or it could be late on both days. So we could work out those 3 probabilities and then add them together. But again, what's going to be quicker with this is to work out the probability it's not late on either day and then take that away from 1. So the probability it's not late is 0.8 times 0.8. So the probability it's late on at least one of these days is going to be 0.36. And it's fine to leave that just as a decimal. Have a go with the first task. Work through, I think there's 4 questions in there. They do get increasingly difficult. If you feel really confident with them, maybe just do numbers 2 and 4 in there. Now, for this example, we're not going to use a probability tree. The next task has got some mixed problems in it. Some of them will need probability trees, some of them won't. And if you did the extension yesterday, this kind of problem will look familiar. And feel free to jump straight into the questions if you feel happy with this. So we've got a bag containing just blue and orange counters. And the ratio of blue to orange is 1:2. So that means in the bag at the start, we could have 1 blue out of a total of 3. So 1 blue, 2 orange. 3 in total, or it could be 2 blue out of a total of 6, or it could be 3 blue out of a total of 9. We don't know. But a useful way we can write this is x over 3x, and look back to the original fraction here if you're not sure where that came from. Now we're then told that 3 more blue counters and 1 more orange counter are added. So in our fraction here, the numerator is standing for the number of blue counters, and 3x is the total number of counters here. So if we're adding 3 more blue counters, we're going to have x plus 3 on top. The total, which was 3x, we're adding 3 more blue and 1 more orange. And then we can tidy this up. And we're told that the probability now of taking a blue counter is 2/5. So this is equal to 2/5. And what we need to do is to solve this to find the value of x for the next step. So if we multiply both sides by 3x plus 4 and both sides by 5, we then need to multiply out these brackets and solve this equation. And that gives us that x is equal to 7. So we're asked for how many of each colour were in the bag at the start. So at the start, we said blue was x. So at the start, there were 7 blues. There were 3x in total, so 2x of those were orange. So that gives us 14 more orange. And it's really useful just to check that these answers make sense. So let's think. So at the beginning, if we had 7 blues and 14 orange, the ratio is equivalent to 1 to 2. Yep, happy with that. We then added 3 more blue counters to give us 10 blue. And we added 1 more orange to give us 15 orange. The probability here of picking blue is 10 out of 25, and that's equivalent to 2/5, which is what we're told here. So we can check that the answer we've got makes sense. Have a try with this one. Really similar idea. Follow through the same steps. So we're told here the probability at the start. So in the same way, it could be 2 out of 7 are green, or 4 out of 14 are green, or so on. And a useful way we can represent this for the problem is 2x over 7x. And again, look at this first fraction we've got to see where that came from. From here, the numerator is the number of green and the denominator is the total number. So if 2x of those are green, then red is going to be 5x. So we need to solve to find x, and we set up our equation to do this. We had 2x green. We've now got 8 more greens are added. We had 7x in total on the base. We're told the number of red is doubled. Okay, so let's think. So green, we've now got 2x plus 8. Red, we had 5x, that's been doubled. So if we add 10x, the denominator here gives us the total number of marbles. We can tidy that up. And everything's divisible by 2. So to make it a bit neater and more straightforward for the next step, we can simplify that fraction. Now we're told the probability now of taking a green marble is a quarter. So that algebraic fraction we've just written down is equal to a quarter. So we need to solve it to find x. So if we multiply both sides by 6x plus 4, and multiply both sides by 4, we need to multiply out the brackets and solve this for x. So that will give us 2x is 12, so x is equal to 6. Now, the question we're asked to find here is how many red marbles are in the bag now. So we started off with 5x. The number was doubled, so we've got 10x now, so the number of red should be 60. Now we could just leave it there, but it's worth taking a moment just to check through and see if our numbers make sense. So we started off with 2x green. Now if x is 6, that's 12 green we think to start off with, and 5x, so 30 red to start off with. We added 8 more green. We doubled the number of red. And the probability of green from these would be 20 over 80 in total, which does simplify to a quarter. So we've checked that makes sense and that simplifies. Have a go with task 2. There's some mixed problems in here. The first one's really similar to the one we've just practiced. Other ones, some of them will be using probability trees, some of them won't. Make sure you check your answers and please get in touch if any of the answers still don't make sense. Now, there's a few extension questions after this, but please make sure you get this done and you get this submitted first. So this question here, there's two parts. Big hint in the title of today's lesson, probability trees. It's going to help you to solve these problems. So show your workings nice and clearly and post them into me. It's really useful to see how you're getting on with these. If you've still got a bit of time left in your hours maths lessons, a bit of your brain left, have a try with these next 3 problems. With these, there's also these questions on a PDF attachment in Show My Homework, and the solutions are there as well. Interested to see how you get on with the winning one here. I think that's probably the most interesting for me of the 3 questions. Good luck.